Hello everyone, welcome to Programming Humanoid Robot in Python. In last lecture, we have learned the background of the humanoid robot and the recent development. We have watched the state-of-art videos, but we still saw many robots fall down during operation. So today's lecture, we are learning to solve one very practical but very important problem for our humanoid robot, trying to stand up after falling down. As we learned from last lecture, we want to program our robot to be an intelligent agent, which can be divided to three major parts: sense, think, and act. The sense takes the sensor input to build an understanding of the environment. The think takes the results of the sense to make the plan or decision. Lastly, act makes the action by, for example, moving motors and changing LED lights according to the decision made by think. Today we want to make autonomous standing up behavior. We will apply sense, think, act model to this problem. Let's imagine what the robot has to do to stand up after falling on the floor. First, the robot has to realize what is the situation. Let's say falling facing down the floor or facing to the ceiling, etc. And then the robot has to make the decision to choose the proper motion or proper plan to move the body in order to stand up. And then lastly, the robot has to be able to execute the plan, move the body parts or move the legs and arms accordingly to achieve or to realize the motion. In the end, the robot also has to detect if the target state, standing up, has been achieved. So we can map different stage tasks to our sense, think, and act model and divide it to three subtasks in this lecture. First, we will do posture recognition, which belongs to sense. And then we will use keyframe-based whole body motion control, which generates the motion path plan. This belongs to think. And last action, which is the single joint control. That means it takes the planned motion path to be executed by low-level control. In the end, you have to program all these three parts in your exercises. Let's start with the sense. So first, the robot needs to recognize what is the situation. In these tasks, the situation means what is the current posture of the robot. More specifically, we want to have the robot to have a standing up straight state in the end. So this is the first picture we want to have. Let's say our robot can have other state, like the other picture, maybe sit, maybe lie on the ground. Our task is move the body accordingly to achieve the final state, to move all the starting state to the final state. And if the robot falls down again, the loop will continue. So that is one of the autonomous behavior we want to have for our humanoid robot, it's quite obviously important in soccer game as well as in other applications. Our sense task here is to realize what is the current status or posture of our robot. We have, let's say, in the picture we have 5 different poses defined. By reading the sensor input, the robot should decide which one of these 5 states currently is. The input, what we have are joint angles. We have 25 joints, and also we have IMU sensors, which can tell the robot orientation of the body. So for example, here we know the body is up straight. Here also the body is up straight. The difference is the knee angle are different. And the seat pose also the knee is quite different. And of course the arm joints are also slightly different. And here the big difference is the body angle. So by using IMU, we could roughly determine, let's say, belongs to up straight or falling. And then by using joint angles, we could determine which one it belongs of these 3. This is the simplest way, or we hard-coded our solution. But by this approach, we will have a few practical problems. First, we have so-called boundary problem. Just imagine we have a robot, have a pose, like here. It's kind of in between of these 2 states. And how can you decide which exact point is, let's say, belongs to this state or belongs to seat state? You could say, okay, by compare the angle difference to the reference pose. And then the next question is, what about this threshold? How much difference is accepted? And so on. As you see, we already got many questions. And last but not least, we may have more than 5 different postures. In practice, we may have 10 or more poses. In order to hard-coded categorize them, you may have kind of nested decision functions, which is not easy to maintain and easy to introduce bugs. Just take a step back to look at this problem again. How would you like to formulate this problem? Some hints? Can you find some relation or similarity to other problems you have solved or learned? Can we apply machine learning technology here? Machine learning itself has become very popular and very useful in many domains. And fortunately, we can apply machine learning technology to solve our posture recognition. Applying machine learning technology means we are switching from hard coding, programming, fixed decision makings to data-driven approaches. We can formulate posture recognition problem as a very classic machine learning problem. Yes, you may know it, classification. In this problem, we can formulate that by given a multi-dimensional input of our sensors to classify to be one of our postures. For this classification problem, we can have different machine learning algorithms used. Particularly, we have a nearest neighbor, which actually the method or hard-coded method we mentioned is really similar to this approach, which is find the nearest reference pose, and actually this is a nearest neighbor algorithm which doesn't really learn but remember all the data and then calculate the nearest pose. This is we have not only, let's say, 10 reference points, but hundreds, thousands, and all of them are labeled to one of these 10, and the algorithm just find top nearest ones and then decide to that one. And then there's a more complex algorithm such as artificial neural network or supported vector machine, which do have training phases, which I will demonstrate today. Let's first look at the basic steps for applying machine learning. Maybe you already learned from other lectures. Here I will give you some brief overview. First, we have to collect data. Instead of we are thinking about this or analyze the problem, domain problem, we collecting data. That means the knowledge or the information are included in the data we collected. Instead of we explicitly described or programmed. And machine learning is the approach that garbage in, garbage out, which means if you have really bad data collected, the final results will not work out. So data collection is really important in this case. After collecting the raw data, we have to pre-process it, including one step usually called labeling. So as the supervised learning approach, we have to label the data. So in our cases, by given a pose or by given a state of all sensor inputs, a human as a labeler or supervisor has to label the data, and then finally we can apply our models. So we can build a model and train it on the data we collected. Then we can test or evaluate the performance of our model on the test data. And where the test data come from? Actually, both training data and the test data are coming from the data we just collected. But we have to divide them in two different splits without overlapping. And doing this division or splits will give a fair way to evaluate our performance. Because machine learning algorithms or models are really good at remembering things. So on the training data, you can achieve really good results, and it can just remember the results without actually learning any useful relations or informations. And in the end, if the performance is okay, you are satisfied, we can deploy and test in the real system. In the exercise, you have to train your classification model based on the data we provided. Here is the code folder of the exercise. In the lobed post data, you will get the text file, which contains all the inputs. Each row is one frame, and they are collected from different times, and the file name indicates the posture. We also have some pictures to show roughly the lobed should look like with the pose, to make you easy to understand the posture definition. I will demonstrate the steps we just mentioned in the slides, how we apply machine learning approach here. First is collecting data, since we already have data collected, but maybe they are not sufficient, since these data are collected from real robots, which may different from the simulation, or you want to improve the performance in the simulation. You can collect your own data. We have this notebook and training data, which can help you to collect data and load the data. Next step is build a model and train. You have to complete the task in Learn Posture notebook. And here you can see each section titles actually correspond to the steps we described in slides. And you only have to fill the code where it indicates your code here. And I have another example, or working example, to have really similar steps, but another slightly different problem, which is really famous as well for machine learning, is handwriting digital recognition. So you have there's numbers from 0 to 9, handwritten numbers, we want to classify them. So actually this problem is really similar as the problem we have in the exercises. And with this running example, you can run all the steps already. So first, for data pre-processing, so we load all the data and to split them in the training and test. So let's first load the data. So as you see, the data here is already packed into a NumPy array, which we have is 1,797 samples, and each one has 64 values. Why 64? Actually, we have the picture in 8 times 8, so each pixel, when we flat them, is 64 values. And our target is from 0 to 9, and so as you see here is each number corresponds to each picture. So that is 1,797. Then we can realize it. Then we build our first model. Here we choose the support vector machine for such tasks. It's sufficient already. Of course, you can try more sophisticated models like neural networks, convolutional neural networks. For simplicity, I will only demonstrate the support vector machine here. As you see, we use the implementation from scikit-learn. We import the support vector machine and build the classifier, which has some hyperparameters. And then for learning or training, it's quite straight away. So here actually I take not all the data, but leave the last 500 samples out. So I will take the first 1200 samples for training. So the fit function actually doing the training by input and the target. Then we can try to predict. So since the last 500 samples are not used for training, we can use them as a test dataset. Here I took the last one to test if it is correct. So it's correct, 8. No? This is the prediction of the model, and this is our ground truth label. So of course we can have a better way to evaluate our model. For example, we can estimate the accuracy on the dataset. For example, here is we compute the accuracy on training dataset, which is 100% accuracy. But as I said, the model usually are really good at remembering. So let's see what is about performance on the last 500 samples, which is our test dataset. It is 97, which is still pretty good. So we are confident that our model have learned how to classify handwriting numbers. And there are also other metrics we can use to better evaluate the performance. For example, we can have the precision for each label, and we can have a recall, and the confusion matrix, which is really quite common used for classification. In here is in this diagonal direction is the correct numbers, and in the other values are actually wrong, either false positives. It means here, for example, 0, the first row 0 is recognized as 4. It's wrongly recognized as 4. And here is number 8 recognized, but actually it is number 2. It should be number 2, but it recognized as number 8. So, and from this matrix we can easily to understand, let's say some class are easy to be confused with another class, or there's some correlation between two classes. Okay, we have trained and evaluated and satisfied with our model. Then we want to save our model. In Python, it's rather easy here. We can just serialize the model to file. Here is actually it's not really saved to file, but instead I saved it to as a string serialized, which you can save to the file and load later. And then I load the model I just saved back with another name, and then do the test. So it means we can load this model in another Python file. And for your exercise, you will exactly following the steps, but with different data, and of course, maybe with different model. But in our experiment, support vector machine is sufficient here. Alright, you just have learned how to train your first machine learning model for our robot. Next, we will take the model output to make our decisions in order to achieve our goal, that is standing up. But before that, we also have to learn how to control the robot. First, let's take a look at the motor of the robot.